Ever wondered what drives the flow of electricity in your devices? Well, let's dive into the fascinating world of electromagnetism to find out. You see, the hero of our story here is something called the electromotive force, or EMF for short. Now, don't let the name fool you. Contrary to what it suggests, it's not a physical force like gravity or friction. It's a special kind of energy per unit charge. Think of it this way. Imagine you're at a water park. The water slide, that's your electrical circuit. The water, those are your electrons. Now, what gets the water moving? That's right, the pump. In an electrical circuit, EMF is like that pump. It's the work done by the source in moving a unit positive charge around a closed loop in the circuit. So, in essence, EMF is the push that initiates electron movement in a circuit. Stay tuned as we delve deeper into this electrifying topic. Now you might ask, where does this EMF come from? Well, EMF is generated from sources like batteries or generators. It's fascinating to understand that these sources convert different forms of energy into electrical energy, creating EMF. Let's take a battery, for instance. Inside a battery, a chemical reaction is taking place. This chemical energy is then converted into electrical energy, which produces an electromotive force. On the other hand, generators primarily use mechanical energy. When a coil of wire spins in a magnetic field, it induces a flow of electrons. The mechanical energy of the spinning coil is thus transformed into electrical energy, creating electromotive force. Solar panels are another interesting source. They convert light energy or photons directly into electrical energy using the photovoltaic effect, thereby generating EMF. In essence, whether it's a battery, a generator, or a solar panel, the principle is the same, converting one form of energy into electrical energy. Different sources, same result, the creation of EMF that powers our circuits. Scene script. Time to see EMF in action in a simple circuit. Imagine a simple circuit consisting of a battery and a resistor. The battery is the primary source of our electromotive force, or EMF, and the resistor, well, it resists the flow of the current. Now, let's delve deeper. The battery, our EMF source, contains a chemical reaction that generates a force. This force nudges the electrons, causing them to move from the negative terminal to the positive terminal. The strength of this push is the EMF. However, our electrons meet an obstacle in their path, the resistor. As the name suggests, the resistor resists the flow of electrons, slowing them down. This resistance is like a hurdle in a track race, making the path a bit more challenging for our electron runners. But the EMF doesn't give up that easily. It continues to push, providing the necessary energy to overcome the resistance. This push and pull between the EMF and the resistance is what keeps the current flowing in the circuit. The electrons driven by the EMF continue their journey around the circuit, powering our devices along the way. Now, you might be wondering what happens if we increase the resistance. Well, the EMF has to work harder to push the electrons around the circuit. This means the higher the resistance, the lower the current. It's like adding more hurdles to the track race. The more hurdles, the slower the runners. On the other hand, if we increase the EMF, say by using a stronger battery, we give our electrons a bigger push. This means they can overcome the resistance more easily, resulting in a higher current. It's like giving our runners a stronger push at the start of the race. So, in a nutshell, the EMF in a simple circuit is like a driving force, pushing the electrons around the circuit, overcoming the resistance, and maintaining a steady flow of current. And that's how EMF powers a circuit, overcoming resistance to keep electrons moving. But how can we measure this invisible push in a circuit? Well, let's demystify that right now. The formula to calculate electromotive force, or EMF, is quite straightforward. It's the voltage across the open terminals of a battery or a generator. So when we say EMF, we're really talking about voltage. The unit of EMF is the same as that of voltage, which is the volt symbolized as V. Now let's break down this formula. E, the symbol for EMF, equals V, the voltage, minus I, the current, times R, the internal resistance. E stands for EMF. It's the total voltage or energy per unit charge produced by a source. V is the potential difference or voltage. It's the work done per unit charge. I is current, measured in amperes. It's the rate of flow of charge. R is the internal resistance of the source. It's like a roadblock that resists the flow of electrons. So, the formula E equals sign V here tells us that the EMF is equal to the external voltage across the terminals of the source of the current and the internal resistance. It's important to note that this formula assumes that the source is operating in its linear region, meaning the current through the source is directly proportional to the voltage across it. With this formula, you can calculate the EMF in any circuit, anywhere. Let's wrap up what we've learned about EMF. Electromotive force, or EMF, is the energy per unit charge that a source, like a battery or a generator, provides to push electrons around a circuit. It's the unseen force that powers our world, from the smallest gadgets to the largest power grids. The source of EMF can be anything that can generate a difference in potential energy. This could be a chemical reaction in a battery, a magnet moving through a coil of wire, or even light striking a solar panel. Once this EMF is generated, it plays a crucial role in circuits. It's the driving force that pushes electrons around, creating an electric current. Without EMF, our circuits would be lifeless and our devices useless. Calculating EMF is also straightforward. It's simply the total energy supplied divided by the total charge passed. So, if you know the energy and the charge, you can easily find the EMF. EMF isn't just a concept locked away in engineering textbooks. It's a fundamental principle that powers our everyday lives. It's what allows your phone to function when you switch it on, and it's what enables power plants to generate electricity that lights up our cities. So the next time you switch on a device, remember the unseen push of EMF that makes it all possible.